Greetings everyone. I've got some lecture demonstrations today. We're going to be starting to talk about rotations, and the easiest way to learn about rotations is to actually have things that rotate. First, I've got a stick. Okay, what good is a stick for? Well, we can look at how the stick rotates. There's two ways to rotate the stick. One, going like this, through an axis that is perpendicular to the length of the stick. And the other way to rotate it is like this, parallel, through an axis that's parallel to the length of the stick. Well, both times I'm just rotating the stick. The stick doesn't have a mass that changes. The mass of the stick is constant. But, nevertheless, it is somewhat more difficult to rotate the stick this way than it is to rotate the stick this way. You can see that I can rotate the stick this way very quickly, whereas if I rotate this very quickly, it's probably going to knock something over in my house. I don't want to have that. But it is somewhat more difficult to rotate the stick this way. Now, why is that? Nothing about the stick changes when I change the axis through which it's rotating from one to another. So why would it be more difficult to rotate in one way than the other? Well, we've got to think about where the atoms are and how the atoms are moving, how each little individual point of mass is moving in an object like this. When I rotate it this way, the atoms that are all along the length of the stick have to all make circles around my hand. And the atoms all the way out here have to make very large circles as I rotate this. The atoms on the ends of this are moving a whole bunch to move in this circle. Even the atoms here or here are moving actually somewhat significantly as it goes around the circle. Whereas, if I rotate it like this, then you can think about the atoms in the stick. Even at the surface of the stick, they don't have to move very far in order to move in the complete circle. Going like this, the atoms are moving very, very far. Going like this, the atoms aren't moving very far. And so because they're not moving as far, you can move them faster through that. Faster in radians per second, in angular velocity. You can put them through several full circles very, very quickly because that's not very much distance that you're going through. Whereas rotating like this, well, going through one whole circle, that is a much larger distance that they're going through. So rotating something along a different axis can change dramatically how difficult it is to rotate that object. We've got some other examples of that. If I take this object and this object, two cylinders, they're the same material, but obviously very different sizes. And because they're the same material but different sizes, they must have very different masses as well. So they're different masses. They are, in fact, different widths right there, if you can see that. So different masses and different widths. Well, which one do you think would reach the books first? If I let them both go up here, which one will reach the books first? I want you to think about that for a second and decide what you think, which one, the large one or the small one, which one will hit the books first, given that this one is larger and heavier, this one is smaller and lighter, this one is thicker than this one. Go ahead and think about which one you think will hit the books first. That's making a hypothesis, and that's all about science right there. Okay, has everyone got an opinion on that? Let's try it. If I take these, line them up pretty well, and let them go. Well, it sure looked like to me that they hit the books at the same time. The fact that they are different masses, different radii, different thicknesses, that didn't actually change anything. They both reached the bottom at the same time. Well, what about this? Now I've got this solid, one material, this hollow, a different material. They are the same radius, but obviously a very different distribution of mass. Think about what we were talking about with the stick, that when all the atoms are on the outside edge, it's more difficult to rotate because you have to rotate those atoms through a larger distance. And also think about how different masses don't really make that much of a difference, and different sizes don't make much of a difference. So I want you to think, which one is going to reach the books first? The solid cylinder or the hollow cylinder? Okay. If everyone has made a hypothesis about that, let's test it. Very, very clearly, the solid cylinder reached the books well before the hollow cylinder. Is that what you were expecting? It's an interesting result that the solid one would reach the bottom faster than the hollow one. Why is that? Well, previously we showed that it doesn't matter the size or the mass or anything like that. But the distribution of the mass should make a big difference. Here, all the mass is distributed far away, so all of the atoms in this are having to move a very large distance as the whole apparatus rolls down the hill. Whereas here, there's a whole bunch of atoms that are near the center. They don't have to rotate very far in order for the entire disk to go down the ramp. That's the advantage that this one has. The atoms in this don't have to, some of the atoms, don't have to move as far as the entire object rolls down. Now, in physics terms, the difference between these objects is that they have different moments of inertia. A moment of inertia is a measure of how difficult it is for something to rotate. And you can even get different moments of inertia when you've got one object that you rotate through one axis versus rotating it through a different axis. Different axes of rotation will have different moments of inertia because, again, moment of inertia is just a measure of how difficult it is to rotate. If the atoms are farther out, then it's more difficult to rotate, and the moment of inertia is greater. Greater moment of inertia means atoms are farther out and it's more difficult to rotate. All those concepts go together. Atoms that are closer to the center are easier to rotate because they don't have to go through as large of a distance, and so the moment of inertia is smaller when you have more mass closer to the center. If you have more mass closer to the center, then you've got a smaller moment of inertia because it is easier to rotate. Now, let's start doing math with all this. Clearly, some objects are more difficult to rotate than other objects because of the distribution of their mass. How do we turn this into something more mathematical? Well, we use something called the moment of inertia. We use the letter capital I to express the moment of inertia, and that is equal to the sum of all the individual mass components times the distance that mass component is from the center of rotation. R is the distance to the center of rotation, to some axis. If you have some axis around which something is rotating, like this is, that dotted line is the axis. You have some axis around which something is rotating. Well, you have to look at all the individual atoms, all the individual mass components, and find how far away each individual mass component is from the center of rotation. So as this is rotated around, the distance from the center of rotation to each individual point of mass is going to give you that R right there. We can also turn this into an integral form, and that's just integrating over the infinitesimal masses with respect to the distance they are from that center of rotation, that axis of rotation squared. As you can probably guess, the units of moment of inertia should be kilograms meters squared. Kilograms meters squared, just as you would expect. Now, we don't really want to have to take each object that we're rotating and calculate this for it. We don't want to, for every single object, find out the moment of inertia using calculus or even just using a summation. Fortunately, other people have gone around and actually calculated the moments of inertia for various shaped objects. You can find the list of those from the book. This table shows the moments of inertia for various objects, calculated using that integral. We've got slender rod axis through center. If you take, say, a pen and rotate it around like this, axis going through the center of the pen, then you will use the moment of inertia is equal to 1/12 times the mass of the pen times the length of the pen squared. If you are rotating around some other axis like this, that's going to be 1/3 ml squared. If you have some object like this that you're rotating around like that, as shown here, then you can take the length of one side, which is A, the length of another side, which is B, take 1/12 the mass times A squared plus B squared, and that gets you the moment of inertia of an object rotating around like that. Same for an object like this, that'd be rotating like this. You take 1/3 times the mass times A squared. A, if it's rotating like this, A is this distance right there. This distance is A, this distance is B. B doesn't factor into this at all. The length this way doesn't matter, it's only the length this way, and that makes sense. The length this way is just going to increase the mass. Making it longer this way will increase the mass, but we've already got the mass taken care of right there. Making it longer this way will change how far away the individual atoms are from the center of rotation. So if we did this and moved it like that, this should have a different moment of inertia. Now, think for a second, should it have a greater moment of inertia or a smaller moment of inertia? This version versus this version. I'll give you a second to think about that. All right, this way should have a greater moment of inertia than this way. This way should be easier than this way to rotate. And that's because the atoms are farther out on this, and so it takes more effort to move them around than it does when the object is shorter, like that. We have hollow cylinder right here. We've got a solid cylinder. Solid cylinders, just like the puck that I rolled down that ramp, 1/2 mr squared, 1/2 times the mass of the puck times the radius squared, or a thin-walled hollow cylinder, just like the thin-walled hollow cylinder, or hoop. Many books call it a hoop, which is just I is equal to mr squared. A solid sphere be 2/5 mr squared, and a thin-walled hollow sphere, so an empty sphere, like a basketball, 2/3 mr squared. Well, there's a whole lot of things here to memorize. Even in normal times, I would never ask you to memorize all of these equations. You can always look them up on the internet. So there's no point in memorizing something that you can look up on the internet. Therefore, I'm going to give you these equations whenever you need them in any test. And there's one more equation that I wanted to present. It's I is equal to mr squared. This I is equal to mr squared is for any time you have an object that is being rotated through an axis that does not go through it. Now that's kind of confusing. So imagine this. Take a water bottle in your hand, stretch out your arm as far as it'll go, stand up, and just start rotating around, rotating yourself around, rotating your whole body around with your arm outstretched with the water bottle in your arm. If you want to find the moment of inertia of that water bottle in your hand, you'll use you'll use I is equal to mr squared. You'll use I is equal to mr squared for any object that is being rotated through an axis that doesn't go through it. When you are turning around, when you are spinning around, the axis of rotation goes through the middle of you. It does not go through that water bottle, which is in your outstretched arm. Therefore, anything that you are rotating, the axis does not go through that object, you just use mr squared. And we'll very often use mr squared for a lot of different objects that we're going to be rotating. So remember this one as well for any object where the axis does not go through it. Let's do an example of calculating the moment of inertia for an arbitrary object. I've drawn this thing out, this strange apparatus. It is made of 2 rods with 4 spheres, one at the end of each rod. The rod here, length 2 meters, length 2 meters, 4 meters, 4 meters. Each object has a mass of 3 kilograms, and let's give each a radius of 0.1 meters or 10 centimeters. There are 3 very obvious axes through which we can rotate this. One axis, axis 1, would be rotating it around like this. Axis 1 would be rotating it around like that. And so these 2 spheres would spin in place, while these 2 spheres would tumble end over end. Alternatively, we could rotate it through axis 2, rotating it around like that, so that these 2 spheres would rotate approximately in place, and these 2 would come up and down under the table, and up and down and up and down. Another axis that we could rotate it through is axis 3, going right through the middle of both rods. Axis 3 would be everything just kind of spinning around like this in the plane of the paper. So, to help you visualize this, we can just take the piece of paper and rotate it like this through axis 1, or rotate it like this through axis 2, or rotate it like this through axis 3. Those are the 3 types of rotations that we can do very easily with this. Well, we should figure out the moment of inertia of this apparatus through all 3 of those axes. And I'll save this over here for a second. To calculate this, let's start with axis 1. Axis 1 is the axis here. And to do this, we need to figure out the total moment of inertia. But the total moment of inertia, remember, moment of inertia is going to be the sum of mr squared. This is the general form of the moment of inertia, the general summation form. This indicates that if we have multiple objects denoted by I, we can sum over each object that we have. If we know the individual moments of inertia of each individual object, then we can just sum over every object. So we can convert this to the moment of inertia total is equal to the sum of all of the individual moments of inertia of every object. If we can find the moment of inertia of each of these objects around each given axis, starting with axis 1, then we can find the moment of inertia around axis 1, and then around axis 2, and then around axis 3. Let's do that for axis 1. Moment of inertia around axis 1 is going to be the moment of inertia of object A plus the moment of inertia of object B plus the moment of inertia of object C plus the moment of inertia of object D. A, B, C, D. Moment of inertia around axis 1 is going to be the moment of inertia of A. Moment of inertia of A. Well, this axis, axis 1, is going right through A. And I said that A is a sphere with a mass of 3 kilograms and a radius of 0.1 meters. The moment of inertia of a sphere, according to the book, is 2/5 mr squared. Now, which r are we talking about for this sphere? Before we continue on, which r are we talking about? I want you to think about that for a second, looking at the diagram. Which r are we talking about for the sphere? Well, we're talking about the radius of the sphere. Whatever the radius of the sphere is, that's going to be the r that we use here. The axis of rotation, axis 1, is going right through the sphere. Therefore, we can use the regular moment of inertia for a sphere, and the radius in that equation is the radius of that particular sphere. So I'm going to make this a tiny subscript s on there to remind me that it's the radius of the sphere. Okay, we need to add the moment of inertia of object B. Well, if we're looking at axis 1 as it rotates around, B is not, the axis does not go through B, nor does it go through D. Therefore, we need to use our moment of inertia when we have an object going around in a circle and that the axis of rotation does not go through that object. So that's just going to be mr squared. And then what radius are we going to use for this? I'll give you a second to think about that. Well, we have to use the radius that that object is from the center of rotation. Object B is 2 meters to the center of rotation. So I'm going to remind myself of that by putting a tiny subscript 2 on there. Now I know a lot of you are thinking, well, what about the 0.1 meters that we're going to have right there? Shouldn't it be 2.1 meters? Well, I'm just going to say that the 2 meters is the distance from the axis of rotation to the center of that sphere. So use that. It's just 2 meters from the axis of rotation to the center of the sphere. Well, moment of inertia of C, that's C right there, that should be the exact same as for A. So we've got 2/5 mrs squared, the s being because that's the radius of the sphere. And then object D down here should be the same as B, which is plus mr2 squared, the 2 being for the 2 meters that the center of D is from the axis of rotation. We can plug in some numbers. I1 is equal to 2/5 times 3 kilograms times the radius of the sphere, I said that the radius of the sphere is 0.1 meters, 0.1 squared, plus mass of the sphere, 3 kilograms, times radius to the center of rotation, 2 meters, 2 meters squared, plus 2/5 times mass 3 times radius of the sphere, 0.1 squared, plus 3 times 2 squared. We see that these terms are the same and these terms are the same for A and C and then B and D, which is what we'd expect, A and C versus B and D. So we can combine those. I'm going to combine A and C together here to 4/5 times 3 times 0.1 squared, plus, and then I'll combine these two, 2 times 3 times 2 squared. Okay, what is 4/5 times 3 times 0.1 squared? Well, 4/5 is the same as 0.8 times 3 times 0.01. 0.1 squared is 0.01. And then we've got 2 times 3 times 2 squared. 2 squared is 4, times 2 is 8. 8 times 3 is 24. So what is this? I1 is equal to 0.8 times 3 times 0.01. Well, 0.8 times 3 is 2.4 times 0.01 is going to be 0.024 plus 24. Therefore, the answer that we get is 24.024 kilograms meters squared. You can tell that the contribution from the spheres that are on the axis, that was the 0.024. That hardly matters. In fact, if I tell you to answer just 3 significant figures, then you're just going to say 24.0 kilograms meters squared. That completely gets taken out by rounding. Very often, when we have objects like this, we'll see that objects that are on the axis of rotation contribute effectively nothing to the overall moment of inertia, whereas objects that are off of the axis of rotation will contribute the most to the moment of inertia. This has to be true. Moment of inertia is a measurement of how difficult it is to rotate an object. Moment of inertia is how difficult it is to rotate an object. When objects are close to the center of rotation, they're very easy to rotate. When objects are very far from the center of rotation, they're much more difficult to rotate. If you're trying to spin that sphere there, then you can spin that sphere very, very quickly, many, many times per second. Whereas if you're trying to spin these at the same rate, you'd have to use a lot more effort to spin them many times per second. Remember that the moment of inertia is the difficulty in rotating an object. The more difficult it is to rotate an object, the greater its moment of inertia. Again, the more difficult that it is to rotate an object, the greater the moment of inertia. Increasing the mass of that object will increase the moment of inertia, but more importantly, increasing the radius will increase the moment of inertia even more because it gets squared. So if you're trying to make something difficult to rotate, then you want large radii and also a large mass, but the large radii is going to end up being the most important thing. If you want an object to be easy to rotate, then you want to have small radius. This is just the same as when I was rotating that stick, and I could rotate the stick like this, or I could rotate the stick like this, and we determined that it was easier to rotate the stick like this than it was like this, around like that, because when you have the stick like this, then the atoms in the object are not having to move very far as it rotates around. Whereas if you're trying to rotate it around like this, then the atoms are having to move quite a bit farther as they go around. So remember that the moment of inertia is a measurement of how difficult it is to rotate an object. Now that we've done all that math about the rotation around axis 1, finding the moment of inertia around axis 1, I want you to think for a second about whether the moment of inertia around axis 2 will be greater than or less than the moment of inertia around axis 1. Remember, the moment of inertia is how difficult it is to rotate something. Therefore, if you rotate something around axis 1, rotate this object around axis 1, this axis, versus this axis here, rotating it that way, which way is more difficult to rotate, remembering that the moment of inertia ends up being the sum of the masses times the radii squared. Which way is it going to be more difficult to rotate? And therefore, which way is it going to have a greater moment of inertia? I will give you a few seconds to think about that and pause the video if you need to. Okay, I think that it's going to be much more difficult to rotate around axis 2, excuse me, around axis 2 than it would be to rotate around axis 1. Around axis 1, these two objects have almost no effect, but these two have some effect. So these are the ones that are going to matter. When we rotate it around this way, around axis 2, then objects A and C are going to have to be moving very, very far to go around. B and D won't have to do hardly anything, but A and C are going to have to go even farther than B and D were in the previous example. So axis 2 should give us a greater moment of inertia than we had for axis 1. Now, what do you think about axis 3, just to get ahead of ourselves a little bit? Is axis 3 going to be greater than or less than axis 1 or axis 2? I'll give you a second to think about that. I think that axis 3 is going to be the most out of all of them, because in axis 1, you've just got these two objects that are rotating around like that with a 2-meter distance. Axis 2, you've got these two objects rotating around with a 4-meter distance. But axis 3, going through the center and rotating it around like this, well, you've got these two at a radius of 2 and these two at a radius of 4. So we should see that axis 3 will give us the greatest moment of inertia of any of those because of the greater distances to the center and two sets of objects that are having to rotate around the center. Let's go ahead and calculate this for axis 2. Moment of inertia around axis 2 is going to be the moment of inertia of A plus the moment of inertia of B plus the moment of inertia of C plus the moment of inertia of D. Remember, we can always just add up the individual moments of inertia of every object. This is going to be object A. Let's see, we're rotating it around axis 2 now. So object A and object C are going to be moving quite far around in their circle. So that means that we're going to use I is equal to mr squared for those two. So we've got mr squared, and this is, what subscript should I give it? Well, I need to remind myself that it's just 4 meters. So I'll put a little subscript 4 there, plus moment of inertia of B. Well, this is going to be what we had for A in the last one, where the moment of the axis of rotation is going right through sphere B. So this is going to be 2/5 r squared, and this is the radius of the sphere. Plus, well, C is going to be the same as A. C and A will have the same thing, rotating around this axis. It's going to be mr4 squared, plus object D is going to just be the same as object B. rotating it around this axis. So 2/5 m r sphere squared. We can plug in numbers. 3 times 4 squared plus 2/5 times 3 times radius of the sphere was 0.1 meters. 0.1 squared plus 3 times 4 squared plus 2/5 times 3 times 0.1 squared. Skipping ahead to the math, we've got 4 squared is 16 times 3 gets you 48. 2/5 is 0.4 times 3 times 0.1 squared is going to give you 0.012. 48, 0.012. You take those, you get 96 plus 0.024. You get 96.024 kilograms meters squared. Again, same thing. The contribution from A and C, the objects that are far from the center of rotation, is going to completely swamp out the contribution from B and D, the objects that are on the axis of rotation. Keep that in mind as you do problems. This would end up getting approximated to 96.0 kilograms meters squared when we apply 3 significant figures. And so the contribution from B and D was nothing, in effect, nothing compared to that 96. We also see that that is double what we got for the previous one. Not double, factor of 4, excuse me. Factor of 4, the previous one, because if we're taking the radius squared in a lot of these equations, we effectively went from a radius of 2 to a radius of 4. Originally we had those two objects doing the bulk of the rotation. We went from that to these two objects doing the bulk of the rotation. So we doubled the radius, and that ended up getting squared, and so we have 4 times the moment of inertia. That means that it is 4 times as difficult to rotate around this way than it is to rotate around this way. Let's do this one last time for axis 3. Remember, axis 3 is this axis going through the center there. We can rotate it through that axis. If we can figure out the moment of inertia through that axis, we can figure out how difficult it's going to be to rotate through that axis. The moment of inertia around axis 3 is going to be the moment of inertia of A around axis 3 plus the moment of inertia of B around axis 3 plus the moment of inertia of C around axis 3 plus the moment of inertia of D around axis 3. Moment of inertia of A around axis 3, well, if we're going like this, does that axis go through A? Well, very clearly not. It does not go through A. A is all the way over here, and the axis is going straight down through the page. So, we're going to use our very convenient equation, I is equal to mr squared. Mr squared. Which r is this? Well, that r is going to be the distance to the center of rotation, 4 meters. So I can write to remind myself that that's going to be 4 meters, plus moment of inertia of B, same story. If that is our axis of rotation, that is certainly not going through object B, and so we can say that this is just going to be, again, I is equal to mr squared, which is the equation that we always use if the axis of rotation does not go through the object. mr2 squared plus mr4 squared plus mr2 squared for C and D. C and D, same as A and B. Well, the masses are all 3 kilograms, and R4, so I can distribute that out. R4 is just 4 meters, so 4 meters squared is going to be 16, plus, that was 2 squared, which is 4, plus 16 plus 4. plus 4 is 20, so that's going to be 40. So 3 times 40 is just 120 kilograms meters squared. That is the moment of inertia around axis 3. Axis 1, it was 24. Axis 2, it was 96. You'll notice that actually the 24 plus the 96 is equal to the 120, which is mostly actually just a coincidence. It's not actually saying anything that interesting, but it's neat. Therefore, we have shown that the moment of inertia around axis 3 is greater than the moment of inertia around axis 2, which is greater than the moment of inertia around axis 1. Please remember to follow along with all this stuff from the book and from the lecture notes that I have for this section. This section is the 115 rotations set of slides. So please go through that set of slides, 115 rotations set. I give a very different example there. In that, I give you this example, example 9.6 in the book. So if you use a different edition than I do, then just look for this funny looking shape and find that in the book, and you can follow along with exactly what I did and figure out the moment of inertia of this object through various axes. I decided that this example that I gave you just now was, in my opinion, less ridiculous than this crazy contraption. This thing is at least a little bit easier to visualize than that. But please follow along with the book and with the online lecture notes that I've posted. I also have some videos in those online lecture notes. You should watch those videos as we go through the lecture notes, because I think that they are sufficiently interesting to show a lot of the principles that we're talking about. So watch those watch those videos in the lecture notes, go through all the lecture notes and do all the problems from there, do the problems from the book, look at all of the information that you're getting in all these different methods, and that should help you study quite a bit. One more thing that I wanted to talk about this video is, unfortunately, the resolution of this camera isn't great, but hopefully you can see all of these equations there. Notice that in each and every one of them, it's always a fraction times a mass times some kind of distance term squared. Fraction, so it's 1/12 ml squared, fraction mass length squared, 1/3 ml squared, fraction mass length squared, 1/12 mass a squared plus b squared. Well, that's still going to be a length squared. 1/3 m a squared, a fraction times a mass times a length a is the length there, squared. Every single one of these is some fraction times some mass times some distance squared. And the reason for that is they all come from the sum of all the individual masses times the radii squared. Keep that in mind as you're doing these kinds of problems, and that will help you to organize it in your brain